This broken clock. My clock broke today. So I gotta get it repaired. Gotta take it apart and fix it. This one I'm going to call Digi. Okay. Break all my levers down to play Philip Wesley's Equestrian Dreams. I think I have 1 minute left. Is that, do I have 1 minute left?
That's right. Just a few seconds on the clock.
Okay, let's see. I'll do a little bit of an kind of an island theme feel. Let's see. Okay, thank you.
Thank you very, very much, Kim. That was really very much appreciated.
Thank you so much.
And welcome everybody to the February meeting for Orange County Astronomers. We've got a small crowd gathering here at Chapman Auditorium. And I know there are others of you out there in the electronic universe. Welcome to all of you. For those of us that are more in the Southern California area and who may be thinking about going out to Anza for the star party tomorrow night, I just thought I would give you an update on a couple of things. One is the temperatures are likely to be very low in the 30s or the 20s. If you're going out there, please be prepared. And if you're planning to leave during the night, please be aware there may be patches of ice on the road and drive very carefully. Scene is not going to be great. It looks like, so it's probably not the best night to go out there if you've got a choice. We did have a problem this week because of the freeze with a broken pipe to our well, and that has now been repaired. So we do have our water system back online. And I guess that's my immediate announcements. I'm not trying to take the torch away from our great announcement guru. I'm sorry? Oh, there has been a question about the condition of the roads. Gary Shones was able to repair the really bad damage that was in the road leading up to the entrance of Anza House, or of the Anza site. There had been a deep gorge that was cut across our driveway. That has now been repaired, and hopefully the repair will last for the season. And the others that have taken responsibility for the roads on the way in have done repairs along that way too. So at this point, the dirt road access is pretty good. Okay, and again, welcome everybody. And I think with no further ado, I will turn this over to Kyle Graham for our regular announcements. Thanks, Kyle. Take it away.
Yeah. Here we go. All right. All right. So first I'll say welcome new members. I believe badges will be still be mailed to everyone. Do correct me, Barbara, though, if they will be put in person on the whiteboard. That can't see.
Please preparing the whiteboard even as you speak for
All
those
right.
of us that are here.
So yeah, if you're there, the name badge will either be on the board this month or next month, depending on when you joined. Our election results are in, and the board is the same as it was last year. So we are excited to welcome them to serve another annual term. Star Parties, I think Barbara gave you the update on ANZA. The local Orange County Star Party, there's still need to be some issues sorted out there with the county, so those haven't resumed yet. Astrophysics and the beginners class are meeting at the Heritage Museum at their normal times. The dates are listed there. The board meeting is online March 5th, 10:30. You can check the OCA website for that information and for information on any of the other events that are listed here. We have found a new outreach coordinator, Jeff Gray. He will be taking over the outreach program. You can contact Jeff using the email listed there, outreach@ocastronomers.org. And the coffee stand is open for those of you who are in the auditorium in person. Right up top, you can get coffee, donuts, and water. Every item is $1 each, and it's up by the library entrance. The Adopt-a-Scope program is ongoing. You can, on the website, as it's shown you there, you can go under resources, Adopt-a-Scope, and see the adoption agreement. And you can also download the current inventory. And on the web page there, there's some more information about the program as well. If you have any items that you think would be interesting to put in the Serious Astronomer newsletter, please write to Dave Fisher at newsletter@ocastronomers.org with those items of interest, and he will review them. Once again, everyone does receive a Serious Astronomer newsletter if you are a member of the club, mailed to your home address. However, if you would like to stop receiving a mailed copy and just access it online, please contact Charlie. Once again, everyone receives a printed copy unless you opt out, and all members are always welcome to access the newsletter in its electronic format on the website. If you do end up making the trip out to ANZA now or pretty soon, please assist in clearing the weeds as needed. And then the next meeting will be held on March 10th. And the WhatsApp presentation is next. Thank you.
Thank you very much, Kyle. We're waiting for the people on the ground. John is there to start the presentation.
Okay, we're just a couple technical difficulties. I think we want us to look a little more brighter. We're that dark patch that you see. Yeah, okay. Okay. Well, the screen's being shown here. Oh, Reza, are we live over the?
Yes, you're live, and we see the dark patch on the screen.
Oh, but do you see the "What's Up" label?
No, not yet. You're
Okay.
not sharing the screen.
Oh, okay. We just need to get my presentation viewable to the remote audience. I appreciate everyone's patience. I'm not doing anything. That was all done by John Hoot here. Are we?
Perfect. It's coming up. We have your presentation in full screen.
Okay, the presentation's displaying on both screens that I know of. So thank you, everyone, for inviting me back to do the What's Up. I really enjoy doing these things. In fact, as I've told people before, this is the only thing that I do that I ever get asked back for. So I sure appreciate the opportunities to do that. Just last night, I went out into the front yard and took a picture of this here. And so I know that makes it look like I just started my presentation yesterday, but I actually started more of it. But this was just some fresh photos I wanted to include to show you where the planets are. And so we've got Venus and Jupiter in the evening. Okay, we just did a little light pollution in our own auditorium. We're going to get that back for everybody. Push the video button. That's what, okay, great. Okay, sorry for the delays. Again, thanks for the patience. Okay, so Jupiter and Venus in the evening sky. I took this picture about 45 minutes after sunset last night to show you where they are now. And a couple nights ago, Venus passed Neptune. So Neptune is going to be sinking lower and lower, and it's pretty much gone for the year as far as high power observations because it's so low in the sky. And Venus is going to be climbing higher. And that in a week from now, it's going to set us up for a couple nice conjunctions with the crescent moon and Jupiter. So on February 21st, the Venus is going to be very close to the moon, and then the moon the next night is going to pass Jupiter. And so that gives you a couple of nice conjunctions to look for, weather permitting, of course. And then by March 2nd, Venus and Jupiter are going to be about a ½ degree apart, which is about the apparent size of the moon. And so if you have a telescope that you can see the whole moon in, you should be able to see Jupiter and Venus together. The Jupiter will be very small and Venus will be even smaller, about half the size of Jupiter, but it'd be worth a look, and it certainly could be fairly easy to photograph. We go up a little higher. There's Jupiter, and the constellation Aries is taking a nosedive right now, and the hoofs of Taurus the bull, you might be able to see them underneath that bar. They're showing up just a little off the edge of the screen. That's Taurus the bull, and about halfway between those two constellations is where I placed the planet Uranus. In this photo, I took a little longer exposure at while it was still the blue hour of the evening, so that's why you get a lot of this blue light. I was hoping I can get Uranus to show up on my picture, and if you zoom into my copy, you can see a tiny little green dot where Uranus is supposed to be. So if we put these photos all together, gives you an idea of where these major planets are right now. Uranus is just under that message that says you are sharing a screen. I'll remember next time not to put anything so high in the picture. But it shows you the planets, Neptune, Venus, Jupiter, and Uranus. And if we go a little farther up in the sky, looking almost straight up, we'll see Aries, but also where Mars is. And here's Taurus the bull, as commonly depicted. And Mars is that little dot right there in this picture that I took yesterday. And Mars was most notable because it got passed by a green comet recently. And I was actually struck by the media enthusiasm for the word green. And so I was thinking, since Mars is always described as ruddy, that would make the comet as gruddy or grunny. So my little joke there. But every now and then the media picks up on a word that the rest of us know. Things like the polar vortex a few years ago suddenly became heard everywhere. Same thing with El Nino. Suddenly the media picked that up and made that a common word. Well, the green comet became very common this year, and I'd never heard much media attention to that color, but I noticed that it seems like comets, a lot of the comets that I've viewed were green. So this one wasn't terribly unusual. About the night, I think about in late January, where the media, was one of the few nights that I could photograph because of the weather's been poor. And so the comet was very green in photographs, but I tried a recreation of what people maybe flocking to see the green comet would actually see in a telescope. And the picture on the right is my effort to dim the image to match exactly how it looked in my Schmidt-Cassegrain telescope the same night that I took the picture, the brighter one, on the screen. So if you go looking for this great green comet, since it's now leaving us and getting dimmer, it's probably going to look a bit like the one on the right, but I hope you...
John, we have lost your voice.
Together a collage of all the green comets that I've photographed since 2009. So I would say every third comet that is bright enough to show up in my telescope on a picture is green. So green isn't a terribly unusual thing, as many of you probably know. But it's fun when the media picks up on something. Here's some photos I took several years ago, and I'm going to use them to illustrate a little more what's in the sky tonight. We've got Orion and Taurus, and right about there's Mars. And this is the path that the green comet took. Hence, I'm using green arrow to show where it passed Mars and where it's going over the next month. And it's going to pass a galaxy called NGC 1637, which is conveniently about the same magnitude that the comet's going to be, or is projected to be at the same time. So it's going to be dim. Both seem dim. I've never looked at 1637, but it might be worth trying to get a photo of those two, see how they show up. Here's Orion. And when I was trying to figure out the maps I was looking at to correlate to this photo I took a couple years ago, I was having a little trouble identifying which star was Pi Orionis. And it turns out that all 6 of those stars in the middle of the screen are all called Pi, and they're numbered 1 through 6. And I thought, well, that's really strange to have so many stars apart, the same designation. That's what I love about astronomy. You never know what you're going to discover. Sometimes you're going to see something outside in the sky. Sometimes you're going to see something on a star chart that you just kind of think, well, how did that get that way? I did a quick lookup and found out that they really are, the star chart wasn't mistaken. They really are all named Pi, and it's exceeded by one other example that I'll come to shortly. But anyway, while you're looking at in that direction, if the comet does not fulfill, you can always look at M42, our Rosette Nebula, the star cluster there. And so you can find the M42 below the belt of Orion as marked here, and the Rosette Nebula. If you follow the head and draw a line through the shoulder, out there is the Rosette Nebula, which shows up really well in photography. So even in this picture, which I took was about a 15-second exposure at a very fast setting, like below f2 probably, and a high ISO, even in 15 seconds, you can see just a little bit of glow of the nebula, which you don't see visually through a telescope, or at least I haven't, but still it makes a great photographic target and a nice thing to look at through the telescope. And if you want cluster and glow, of course, the Pleiades up there at the top of the screen is a great target too. Here's the Pleiades in a field of view comparable to what you might see in a 10-power binocular. And here's a view of the Rosette Nebula. The longer exposure brings out the nebula. You don't see that visually, but you do see the little star cluster in the middle. And here's a view of the Orion Nebula, M42. I took this the same night as the Mars Comet conjunction. The weather wasn't terribly great, but it shows how beautiful things to look at. And now I've moved Orion over up into the left corner of my picture, and to show you a little bit about a constellation just to the lower right of Orion, and that's Eridanus, the river. And next to, and here's where there's the 9 stars, all named Tau. And so, and they are numbered 1 through 9 in the direction downhill of the river, as I portrayed the river. So those are just some neat little oddities about star charts. And anyway, Lepus the hare is just underneath Orion. And near Lepus and in Eridanus are a few things worth hunting down. One is, not too long ago, I read a book about the star Sirius and learned how important that star was in discovering white dwarfs, a white dwarf companion, which I have been able to see in a telescope. And then I learned recently that 40 Eridanus is actually the second white dwarf companion ever discovered. So one of my ambitions is to find out if I can observe it in my own equipment. I actually have no idea how easy that's going to be, but that's what I love about this hobby. You can always just decide something and say, I'm going to try to find that. And succeed or fail, who cares? It's a lot of fun. Near that is a very reddish star, R Leporis, a carbon star. I'll show you a picture of that shortly. There's also a fairly bright small planetary nebula in the area, and that's a dying star that leaves a nebula around it, NGC 1535, and then also a fairly respectable globular cluster, M79 in Lepus the hare. So here's a M79 in an 8-inch Schmidt-Cassegrain. And here's at prime focus, that's how I photographed that. And then same here, 8-inch Schmidt-Cassegrain. I think this one, I don't recall whether I've seen this in my 8-inch scope, but I have a feeling if it's that bright, if I get to a dark enough site, I should be able to see it as a genuinely green object that looks like about a star, but it'll be notable for a little bit of green color. And here's R Leporis in through my 3-inch refractor. And I have no shortage of out of focus pictures, but this one was done deliberately just to emphasize the color of our Leporis. It really is a vivid, brilliant red. And I guess they call them carbon stars. So those stars are old stars, but they've also built up a lot of carbon, which tends to make their light tends to be redder, as I understand them. Anyway, so Eridanus, the river. The constellations over here to the right are all taking nosedives into the western horizon about now. And so I'm going to look a little bit over to the left from here. And here's Canis Major, which reaches its kind of its highest arc in the southern sky about now. And so here's how the constellation is commonly drawn. And here's a couple characters in the sky, Lepus the hare and Canis Major, the big dog. And here's a bunch of names of stars, which I think are beautiful names. I never get tired of looking at constellation in a chart that has star names and finding out, well, what interesting names there are. So it's always fun to look through those. But here are a bunch of deep sky objects. I haven't photographed or observed all of these, but these ones that I'm leaving here, I have. And so I recommend taking a look at them this time of year, since they're going to be reaching one of their highest arcs in the southern sky. And so here's M50, open star cluster. Here's M93, another open star cluster. And M41, a very well-known open star cluster, great in binoculars. And then here's one of my favorites, M46 and 47, and they're my favorites because about 25 years ago, when I first moved to where I live, it was dark enough to walk out my backyard, take a pair of binoculars and go, oh, wow, what's that? That's something I've never seen before. And so I noticed these little fuzzy patches just to the left of Canis Major and eventually hunted them down. And it turns out they're NGC 46 and 47. So it's just fun to make discoveries that way. And NGC 46 has a line of sight planetary nebula that you can see, that green glowing thing. I can't think of the name off the top of my head, but it's in this little, it was one of the ones that I showed on the previous page. And then here is a NGC 2440, and it's the one that looks kind of like a little white dot below another white dot. Doesn't help you out much, but it's a planetary nebula too. And here's another planetary nebula. The noticeable green color. I don't think this one's very easily seen in a telescope, but it shows up very nice in a photograph. And then to the next of it is a open star cluster. And so in this area, that's those objects that I cited. Up there, I don't have it labeled. That one, the NGC object that's in M46, I don't have it labeled, but look to M46, you'll find it. Okay, also taking another picture, pointing up my camera a little higher just to cover things that are in the sky. Orion and Taurus and Canis Major down below. And Canis Minor is over to the left, and Gemini is over to the left. I haven't drawn a picture of Gemini yet, but Gemini is full also of wonderful things to see. It's very high overhead, so it's a good thing to look at. This one here, NGC 2371 and 72 is actually one object, but it got initially cataloged as two separate objects. It's a planetary nebula, very notable two lobes to it. So the two lobes got given their own NGC number. And here's one that you can see in an 80 telescope. And it's really nice because it's right next to a star. And so you can see the star and you can tell that the thing next to the star is definitely not a star. So it gives you that little bit to compare to. That's another planetary nebula. And then I thought I'd end with another object that's in that area in Gemini, M35, a very nice cluster with a much smaller distant cluster in it. But this one I discovered when I was looking for a collection of green comets. I found this comet, this picture I forgot all about that I took back in 2018 of comet 21P actually passing in front of M35. So I thought I'd use that as my example of M35 tonight. And since we do still have a comet in the sky, the last bit of inspiration to see if you can go out and get some pictures of the comet. People have been posting really nice pictures of that comet and C22 E3 ZTF, and they're using like hours and hours of exposure time. 60 seconds gets you something about like what you see on my screen, but a really wonderful object that people have been getting. So I hope you get out and try to see that and photograph it. And that's certainly not all that's in the sky, but it's about all I can cover tonight. Thank you.
Thank you very much, John, for yet another amazing presentation. And speaking of your presentation, actually, let me let the audience know that you've done a TED Talk on light pollution that I strongly encourage everybody interested to go and watch. Hi, my name is Reza, and I'm the Vice President of the club. I, too, would like to welcome you to this general meeting of the Orange County Astronomers on February 17th, 2023. Our speaker at this meeting is an associate professor at the Cosmic Dawn Center and University of Copenhagen, having previously spent time at Caltech, Kavli, Harvard, and Princeton. His research is inspired by astrophysical phenomena whose explanation has been cast into doubt either by new theoretical ideas or new observations. Recently, this includes several different areas of astronomy and astrophysics, including galaxy evolution, black hole accretion, and gamma-ray bursts. Recent work also includes developing machine learning and statistical methods for making full use of the large datasets modern astronomy produces. He also runs a summer undergraduate research program that brings American students to Copenhagen each summer. Please join me in welcoming Dr. Charles Steinhardt. Charles.
Yeah, thank you. Can you hear me?
Yes, we can hear you loud and clear.
Okay, and that sharing hopefully worked.
And let me also mention to the audience that you have access to ask questions during your talk also. So if anybody has questions, you could use the Q&A option on your screen to send the questions during Charles' presentation. Thank you.
Great. Okay. This working?
Yes, we see the presentation all great.
Okay. Great. Yeah. Thanks a lot for inviting me. I really appreciate the invitation and the chance to kind of come visit the group. So I do work on a lot of different things, and I think maybe the most interesting things I found as a scientist and the most exciting are the places where we're discovering that something we really thought we understood suddenly turns out to really be wrong. And that's usually what happens right before, some really good new ideas and something unexpected happens. And so with that in mind, what I thought I would do is tell you a little bit about some of the things that have been happening in our study of galaxy evolution over the past decade or two, and kind of why that's setting us up for the first few years of James Webb to be particularly exciting. So maybe to begin with, just to think about why we're interested. Well, of course, we know that we live in a galaxy, and that this is not some kind of strange occurrence, but that if we look just deeply at the night sky, this is a deep field taken with the Hubble Space Telescope. If we just stare deeply at what otherwise seems to be a blank patch of sky, we actually find that it's filled with galaxies of all different shapes and sizes and colors and structures and so forth. And so it seems that what nature does is generally to make a universe that's filled with galaxies. And this is the natural thing that happens from all of the ingredients that were provided with after the Big Bang. And so the study of galaxy evolution is really trying to understand, how is it that we get to a universe that looks like this? How is it that, on the one hand, galaxies are a common thing that gets made, but on the other hand, galaxies can all look different from each other? And how do these galaxies grow? And for that matter, what causes them to stop growing? So when we think about the story of galaxy evolution, I think it maybe is easiest to think about there really as just kind of being three main steps. So the first thing that happens is we just have to assemble the initial ingredients that are going to become a galaxy. And once all of those ingredients are in the same place, then there are a whole series of things that have to happen to form stars and form a central supermassive black hole and form all of the structures that would make something recognizable as a galaxy. And then finally, we notice that, at least for the most massive galaxies, we notice that by today, most of these processes have stopped. The black hole's not growing anymore. stars are not being formed at a high rate. So there's something where the galaxy kind of dies. And we might guess that these three stages, first assembling the ingredients, then using the ingredients, and then finally kind of being finished using the ingredients, we might guess that these are really governed by different kinds of physical processes. But as much as my work is more on the theoretical side, I should point out that as observers, we actually study these three phases in very different ways as well. That is to say, when we look at the dead galaxies today, this is really the only thing where we can look at galaxies close by. So we see all of these pretty inspirational images of galaxies, and I kind of couldn't give a talk like this and not at least have some pretty picture. This is what we like to think of as a galaxy. This one's M83. But really, we only get to see this for very nearby galaxies where we can resolve all of these structures. And this is something that really we're only getting when we study these dead galaxies. So unfortunately, the distant galaxies that I look at don't look nearly as inspirational. They look something a little bit more like this. And these tiny unresolved blobs are really what the galaxies that I end up studying look like. Maybe if we're lucky, we have a little bit more information because instead of just getting these pictures in a few different filters, we're actually able to take a spectrum. So if we can get a spectrum like this, now there's a lot more information. What we've done here is we've taken, there are probably 1,000 different very narrow wavelength buckets in here. And in every one of those buckets, we've collected enough light to be able to measure the flux. And so we get all of this structure, which I'll come back to in a moment, with different atomic and molecular transitions and ways that you can learn about more details. But even this is what we get only if we're lucky. Something like this for these distant galaxies can take between 1 and 100 hours per galaxy. So we only have these in the relatively uncommon cases. So that's this intermediate stage, this formation stage. If we want to get all the way back into this initial assembly of material, well, there it's even worse. At this point, that's entirely the domain of theory or simulation. And we don't have any direct way as observers of going back and learning about them. And so most of the advances in the past decade or two have really come in this intermediate stage and in pushing back to earlier and earlier times and in growing from catalogs of 100 or 1,000 galaxies to catalogs of 1 million galaxies, where we can just do a lot more science with a lot better statistics and a lot more examples. And so a lot of what we've learned has been about this intermediate stage, this formation stage. Now,
Charles, if I may interrupt you, we are
Please.
seeing the Windows toolbar on your screen. Is there a way to hide that?
Are we? Let me see if I can fix that. Sorry about that.
And by the way, for people who are not aware, Charles is joining us at 5 a.m. Yeah.
Behavior.
Perfect. It's showing all full screen now. Thank you very much. Sorry for interruption.
Good. All right. Let me. Thank you. Okay. So a lot of what we've learned, ideally might come from one of these spectra. And the good news is that a spectrum like this conveys a lot of information in return for taking, hours per object in order to get one. So every one of these different lines that you see, you may be able to see that those are marked, like this one's O3. So that's a particular oxygen transition. This H alpha is a hydrogen transition. And the idea is that these are all things that we can match to what a spectrum looks like in the laboratory. So for example, if we want to find the distant galaxies, we want to find the ones that are at high redshift. I'll notice, I should mention, by the way, that here, the graphic that I got that labeled this a very distant galaxy, this would have a redshift of about 0.3, meaning that the wavelengths are about a factor of 1.3 times as long as they would be in the laboratory frame. The galaxies that I'm going to be showing you that we work with here are at a redshift maybe of 6 or 7, and the ones that we're starting to get from James Webb have redshifts greater than 10. So the idea is that you can take every one of these transitions, so take, for example, a series of hydrogen lines and match them up, and that'll give you the redshift in addition to other properties. So for example, we could look at how many of the hydrogen atoms are in excited states and try to use that to learn something about the conditions in that hydrogen gas. And all of these transitions come from a bunch of underlying physics about what an atom looks like. So for example, in a hydrogen atom, what happens is that as we absorb a photon, you can absorb a photon that lets you jump from one energy level to another. So we have, for example, this Lyman series of lines that are typically in the ultraviolet, where you're jumping from the ground state to a higher energy state. In the visible, you're often seeing a jump instead from the first excited state, from an n=2 state. So you get this whole series of lines. But on the other hand, imagine that we actually give hydrogen a very high energy photon. Well, if you give it a high enough energy photon, it doesn't have to jump to any specific level. It can simply let the electron escape, and it becomes ionized. And so what that means is, if you have light at short enough wavelengths, instead of hydrogen only being able to absorb specific lines corresponding to these transitions, hydrogen can just absorb everything which is high enough energy, everything which is at short enough wavelengths. And so maybe what that means is, maybe if we want to identify a really high redshift galaxy, so the easy way to do it is to take all of the time to get a spectrum like this and find individual lines and match them up and figure out how much they're shifted. But maybe what we could do, imagine just zooming way out for one of these high redshift galaxies. And here's what some of these spectra look like. If we zoom way out, what we see is that the high energy photons, so on the left, the bluer light, have all been absorbed. So you really don't see any emission. On the other hand, at longer wavelengths, lower energies on the right, now you don't have enough energy to ionize hydrogen. Now it's only able to absorb these specific frequencies again. And so you see a bunch of emission. And the thing is, you don't need the whole spectrum to figure out where this Lyman break is in the middle, right? Having zoomed out, you don't need all of the details to pick out the redshift. So maybe what we can do is we can do something a lot quicker. Maybe instead of taking 1,000 different very narrow wavelength bins and counting enough photons in every one to get a spectrum like this, maybe we can just take a few different broad filters. And we can take an image of the sky in, say, 5 different filters here. And if we want to find the high redshift galaxies, all we're looking for are the galaxies where on the right here, you see a bunch of flux, but on the left, it disappears. And this is exactly the example that I'm showing you here. Okay, I'll make it a little bit bigger, just so you can kind of see what's going on. So in the top row, for example, what we see is that in these 2 reddish filters, in J and H band, we do see that there's something right in the center of that circle. But this galaxy seems to disappear when you look at bluer light. And so this dropout technique is a really efficient way of finding these high redshift galaxies. Using that, we've been able, in this example, here are 4 galaxies at redshift 7 that we didn't need to take an expensive, time-consuming spectrum of everything in a large survey to find, but rather are able to find just from this idea of photometry and taking a bunch of filters and looking for the ones that drop out in blue filters but exist in red filters. So the good news is we now have a really efficient way to find some of the earliest galaxies. The bad news is you probably want to do more than just find them. You probably want to figure out a little bit more about what their properties are. By the way, I'm showing you some of the cleanest examples here. The one at the bottom is unfortunately a little bit more typical example, because as we saw, the night sky is crowded and it's filled with galaxies. So the one at the bottom is an example of a more typical problem that we have, where you may see that there are actually two galaxies in that circle. So there's a very high redshift galaxy right at the center of the circle, and that you see only in the reddest bands. But a little bit to the bottom, below and to the left of that, now you see another lower redshift galaxy, which is visible in all 5 bands. And one of the difficult tasks is not just identifying them when they're near each other, but then also being able to really separate the light and figure out, how much belongs to each of the 2 galaxies in order to model them correctly. So the good news is this lets us identify galaxies. The bad news is we really want to do more than just count them. We want to be able to learn about their properties. So the way we do this essentially is to hope that our physical models have become good enough that maybe we can try the problem in the opposite direction. Maybe instead of actually observing a spectrum, what we can do is we can generate physical models, and we can generate a whole series of synthetic spectra where we take models and we figure out what do we think the spectrum would look like from that model. And this is actually just one of a bunch of different parameters that go into this. So for every one of these models, we add more parameters, and then we go ahead and compare it against the observed photometry. And we ask, well, of all of the big models in our enormous space of different possible things galaxies could look like, which one looks the most like the photometry that we observe? And we decide that those are probably the properties of the galaxy.
We have a question here. Yes, the question is concerning about those absorption lines. How do we know they are from the galaxy itself rather than the material sitting between us and the distant galaxy?
That's a good question. So it could be from either. And the easiest way that you would be able to tell the difference with a spectrum is if the absorber is around the galaxy itself, then the redshift of those lines is going to be around the galaxy. And if, for example, one of the places this often comes up is you have a distant quasar, so a supermassive black hole, which, while it's growing, can be one of the most luminous things in the universe. And then maybe you have a molecular cloud that happens to be on the line of sight between us and the quasar, so that it's illuminated by that quasar. What we can often see is a whole series of absorption lines where you'll see lines from the quasar, those will be at the highest redshift, and then you'll see another series of hydrogen lines at a lower redshift, that's an absorber partway in between, and you might even see multiple series if you get really lucky and get several clouds. So you could have different redshifts in the same system along the same line of sight.
And doesn't that interfere with your method of discovering these high redshifted objects? Because then everything is present in all those bands?
Well, so what should be happening is that the lower, so if you have, let's say, for example, you have a redshift 2 galaxy, and there's also a redshift 1 cloud in between. The redshift 1 cloud is going to absorb things that are redshift of 1. And so you're going to see a Lyman break. Everything which would correspond to a redshift 1 Lyman break will disappear. But if there's also hydrogen in the redshift 2 galaxy, then everything out to a redshift of 2, that will also disappear. And of course, that's more stuff. So you just see the redshift 2 Lyman break. So you always see the highest redshift Lyman break. And fortunately, most of the universe is made of hydrogen. So essentially, every galaxy is going to have a Lyman break just associated with that galaxy.
Thank you.
Okay, yeah, thanks. All right, so we're able to fit all these properties, and what this leads us to then is, well, now we have these properties and we can try to put them together and see what they tell us. And I think one of the key discoveries and the thing that first really excited me about this area is something that we've come to call the star-forming main sequence. Now, you've probably run into the stellar main sequence, and unfortunately, despite the name, the stellar main sequence is actually something entirely different, which relates to individual stars, say in the Milky Way or in other galaxies, and how individual stars behave. The star-forming main sequence is instead telling us about how star formation works in galaxies, not in individual stars. And what it's telling us is that if we look at all of these galaxies and the big catalogs that we build, and we look at ones that are all at the same redshift, there's a really tight relationship between the rate at which they're forming new stars on the y-axis here and the existing massive stars they've already formed on the x-axis. And I mention at any given redshift because there's also a time dependence to this. So you get a main sequence at every redshift, but it looks a little bit different at high redshift than low redshift. Now, this may seem like a simple relation, but actually already I should point out that, putting my theory hat on, this is kind of stunning and really hard to explain. So one way we can think about it is the process of making a star involves a competition between gravity, which wants to take a cloud of gas and bring it together and make a star out of it, and thermodynamics, which says, no, the gas is trying to expand instead. And in order to make a star, gravity has to win. But what that means is if I want to know how successful a galaxy will be at making stars, anything that affects this delicate balance between gravity and thermodynamics is going to be important. So anything that affects gravity and anything that affects temperature should be part of this calculation. So imagine I told you I have a galaxy. Your task is to predict the star formation rate. Give me the list of information that you need. Well, I think that would be a long list, or at least you should expect that it would be a long list. So yes, the mass is important because that affects gravity, and the age is probably important. That's probably telling you about some of these factors, but so are many other things. For example, I might want to know, is the central black hole growing and emitting radiation and heating the gas around it? That would change the temperature. Did the galaxy just have a merger so that new material came in or so that things got stirred up? That would affect the temperature. Are there a bunch of young stars in the galaxy that are very luminous and heating everything up? That would affect the temperature. For that matter, did we have a round of star formation a little while ago so that there's now a high supernova rate in the galaxy that heats everything up? I might want to know whether it's a spiral galaxy or an elliptical galaxy, because that might change the heat transport. I might need to know about the composition of the gas, because sort of pristine hydrogen and helium is less efficient at cooling than gas that has more carbon and magnesium mixed in. So you'd really have a long list of questions that you'd like to ask me if I tell you your job is to predict the star formation rate in a galaxy. But observationally, it turns out you don't need to ask me those questions. The only things I need to tell you are how massive the galaxy is and what redshift it's at. And that seems to be enough for you to predict the star formation rate. And we don't know why this is true. But this is a strong observational result, so we know that it is true. And this is kind of one of the puzzles that's been driving me to become interested in kind of trying to explain what's going on. So when I first started looking at this was actually one of a bunch of studies. So there had been something like a dozen different studies. These studies have different ways of kind of attacking the problem, different independent groups, but all of them agreed on the main idea, which is, first off, that at every redshift they tested, they found a main sequence. Second, we found that I mentioned there is a time dependence, that as we go toward high redshift, that everything becomes more efficient. So the star formation rate at the same mass is going up toward high redshift. And maybe this is intuitive. Maybe this simply says that galaxies start out with a lot of material that's able to be made into stars, so they're really efficient at it. And over time, as they use that material up, they just get progressively less efficient. And then there's this last one, which is maybe more of a surprise, which is that if you look at the most massive star-forming galaxies, as we go toward high redshift, they're becoming bigger. So for some reason, if you look at the most massive ones, what's happening is very early in the universe on the left here, you see the biggest ones. So the biggest ones form their stars early, and then they turn off and they die and they're done forming stars. And as we go closer and closer to the present day, it's the lower and lower mass galaxies that are still kind of lagging behind and trying to finish forming. And the most massive ones have already finished and died. And again, it's this one, I'm really not sure why this is true. But again, there's a whole series of different related results showing that this idea of downsizing seems to exist, and that the most massive galaxies seem to go through their stages of evolution more quickly and earlier than the less massive ones. So all of these studies agreed, at least qualitatively, that this is what was happening. But when you looked more closely at the details, it was actually kind of a mess. So for example, if I asked you to describe this relation, maybe the thing you would do is just take the slope of the line. So I showed you those couple dozen results, and here are the slopes of the lines that they get. And this looks like a mess. So on the right, toward the present day, toward local things, maybe there's more agreement about what the slope is. But as we go back in time, as we go toward high redshift, depending upon which of these results you prefer, you might decide that the slope is increasing, or maybe it's decreasing, or maybe it's even constant. But it was kind of unclear what to make of this tangle of results. So Reza had mentioned at the start that I run an undergraduate research program. And if there are any undergrads listening, feel free to get in touch, and I'm happy to point you in the direction of some possible projects. So I had an excellent undergraduate named Josh Spiegel, who's now actually now faculty at the University of Toronto. And the idea that we had, kind of as a summer project, was to maybe see if we could figure out what was going on. Because you remember I said these studies were all done different ways. So for example, they have different ways of determining the star formation rate. In this column on the left, they have a bunch of different ways of just selecting which are star-forming galaxies. So what we thought was, well, maybe what's happening is you have all of these different ways of calibrating things, and they're calibrated in the local universe, so they all agree at late times. But maybe as we go to the early universe, maybe that's starting to break down, and maybe we can find a way to recalibrate it. And so maybe we can kind of repair this problem. Well, it turned out we were actually completely wrong about what was going on. It wasn't this calibration problem, but it was actually kind of the other real difficulty in high redshift astronomy. One difficulty is this lack of ability to resolve things and that everything's faint. But the other more general problem with galaxy observations is what I might call sort of the tip of the iceberg problem, which is that the light that we see from a galaxy is only coming from a very small fraction of its mass. And we have to infer what the rest of this mass below the surface looks like.
Now, yeah,
that's... By the way, it's been pointed out to me, so if you go online and you just take look for an image of an iceberg to put something like this together, this is the kind of image you get. It's been pointed out to me that icebergs don't actually look like this. And there's a wonderful site, if you want to play around with it, called Iceberger, where you can actually draw an iceberg and sort of get a sense of, how it would float. And it actually gets the physics right. So apparently, the iceberg that I showed you here wouldn't float like this. It would tip over. This is unstable, but as much as it's an unrealistic iceberg, it's really good for making a slide. So we'll kind of run with it. The point is that most of the mass in a galaxy essentially is invisible. So, for example, well, actually, the biggest fraction of the mass in one of these galaxies is simply dark matter. And, I don't know what dark matter is. If I could answer that one, I'd go pick up my Nobel Prize. But what I can definitely tell you is that, as the name seems to suggest, it is dark. And so we're not getting light from it. We can't see it. The only way we can infer its presence is from other things that do give off light. Okay, so that's actually the majority of the mass. Then of the remainder, what we call baryons. Again, the light that we see is really starlight, and most of the baryons are not in stars. So in the Milky Way, for example, something like 10% of the baryons eventually made stars, the rest didn't. So that means we'd expect that, 90% of the remaining stuff, again, is going to be invisible. And then finally, even of the stars, remember that the most massive stars are much more luminous than the low mass ones. The luminosity of a star on the main sequence is going as something like mass to the 3.5. So that means a 10 solar mass star is 3,000 times the luminosity of the sun. So what that means is the light that we see isn't coming from most of the stars. We don't see any of the low mass stars. It's dominated by just these rare high mass stars. So in our own Milky Way, most of the light is coming from things larger than the sun, but most of the mass is actually things smaller than the sun. So when you put it all together, we're seeing at most something like a part in 1,000 of the mass of a galaxy. And we have to infer what the rest is. So how do we do this? Well, pretty much the only way we can, okay? We only see the tip of the iceberg. Well, we've got one iceberg we can study really well, which is our own galaxy. So for lack of any better idea, we just assume that all icebergs are made of the same type of ice. So we learn things about the Milky Way, and then we try to scale from what we learn about the Milky Way to, what every other galaxy is going to look like. I mean, what else can we do? And even within the Milky Way, some of these are very hard problems. So for example, I mentioned that the low mass stars are invisible, and we need to figure out how many low mass stars there are. Well, in the Milky Way, this is often described as the problem of finding the initial mass function, which is the mass distribution of stars that you make right at formation. And this has been one of the historically difficult problems over the last century in studies of the Milky Way. And different attempts, kind of all of them say that sort of toward high mass, toward the right here, things are getting rare. But, these various attempts still disagree on the shape. And, often when I show something like this and you see things ranging from, a 1955 paper, 2003, often what you expect is, well, we had models in the past and the models have simply gotten better over time, and now everyone uses the current models. But actually, that's not even true. What we see is these different main sequence studies used a bunch of different versions of the initial mass function, ranging from all the way back to 1955, as still thinking that was the best approximation. Now, I cannot tell you which of these initial mass functions is right. That's a really difficult observational problem. But what I can tell you is that if you pick different IMFs, it's almost like reporting your results in different units. Because what you're doing is you're assuming different types of icebergs when you scale from the bit that you see. But the nice thing is, like different units, we can just pick our favorite set of units and we can just convert all of these studies to one common set of units and then look at them against each other. And this is what Josh did. And suddenly we found they all agree. So this is a little bit different version of the main sequence. I mentioned that there are 3 variables: star formation rate, mass, and time. Here, this is at fixed mass, and we're showing you all of these different studies with star formation rate against time. And you see not only do they agree with each other at the same time, but they even give you a really nice idea of a consistent, decline in how efficient galaxies are at making their stars as over the course of the universe. So as an observer, we should be looking at this and celebrating. We now know what star formation looks like for most of the history of the universe in almost all galaxies. As a theorist, it still bothers me that I can't explain any of this. And not only that, but often in astronomy, when we can't explain something, it's an observational science. What you do is you look for things that are misbehaving. You study those and you try to figure out what's different about them. But this main sequence is so darn universal that it turns out we can't even find good outliers to attack. So for a little while, it looked like we got stuck. And finally, we had this realization. Well, I mentioned before we only knew these things qualitatively. Well, now we know them in a lot of detail. We know exactly how, things are getting more efficient toward high redshift and so forth. But these last two, the galaxies toward high redshift are more and more efficient at making stars, and they're getting more and more massive. That can't go on forever. At some point, you have to get back into this initial assembly phase instead, and then they're going to have to look different. So based on this, we were able to get about 2,500 hours on the Spitzer Space Telescope. So this was the largest, one of these allocations to that time that had ever been given to a single program. And the idea was to figure out what the main sequence looked like when we go back to such early times that this is going to break down. So we spent 3 full months of time on a space telescope. We also spent at least, an additional 3 to 5 years probably of, time of humans to take that data and turn it into something usable. But what it meant was we were finally able to figure out what happens when the star forming main sequence breaks down at high redshift. And the answer is another main sequence. And actually not just any main sequence, but if we take what we had before and we just use it to guess the answer, it's exactly the answer we would have guessed. And, the masses even are exactly the masses we would have guessed. So we spent all of that time on, a large space telescope and so forth, and didn't get anything out of it. We could have guessed the answer. But on the other hand, actually, when we think a little bit more about our understanding of how we assemble the ingredients, actually, this is a pretty stunning answer. So if we think quickly about the story of assembly, the story starts with these tiny fluctuations after the Big Bang. So you may have seen one of these images of the cosmic microwave background, this kind of relic radiation from hundreds of thousands of years after the Big Bang. By the way, this is not what the CMB looks like. The difference between the hot and cold spots here are, the difference between the hot and cold spots here are something like parts per thousand. So really a fair description of what the CMB looks like is this. Okay, the CMB basically is constant, but there are these tiny fluctuations, like thousandths of a degree. And these little hot spots with a little bit of extra material, just because of gravity, they grow and more things fall in. And here's just kind of a simulation of what that looks like, so that you can see that over time or toward lower redshift, what's happening is the universe empties out and most of it becomes empty. And then instead we make these larger and larger structures. I can kind of play that again. So there's this formation process where over time you make structure, starting from little structures. And by the way, this is part of why this era of James Webb is so exciting, because if, at least to me, the most exciting part of a picture like this is somewhere right around here, just as you're kind of having this transition from not having stuff to suddenly having recognizable stuff. And this is exactly the era that we're finally able to probe with James Webb that we weren't able to probe with Hubble. So what we can do if we want to understand assembly is we can just take a simulation like this and we can freeze it somewhere and take a snapshot and just count up all the structures that we see. And then we can maybe compare that to the galaxies that we actually observe. So here's an example of what that looks like. At the top, these are, the top left is sort of the most local, the lowest redshift answer, moving toward bottom right. So the green here are theoretically all of the structures you should be able to make gravitate, just from gravity assembling the ingredients. And the magenta are the galaxies we actually see. So in the top left corner, sort of more locally, what we see is there's this little knee in the curve, maybe where the two agree, where we've been able to use up all the ingredients we have. And everywhere else, galaxies are just not fully efficient. And we think we understand why this is true. We think that there are various feedback mechanisms. So things like supernovae from stars that you've already made, preventing you from making more stars so efficiently, or feedback from the growing black hole that eventually stops galaxies from making stars. And so that's why the magenta curve lies below the green. But these feedback processes take time. So what we thought might happen is that as you go earlier in the universe where there hasn't been as much time, the shape should be more and more similar and the magenta curve should look like the green. And that's kind of, broadly speaking, what's happening if you kind of squint a little bit, But there's one little annoying problem if you look at the very highest mass objects, the ones furthest to the right on every plot. Because those just keep moving to the right, and somewhere around the third to last or maybe second to last panel, around a redshift of 3 or 4, they agree. But then in that last panel, now that magenta curve is to the right of the green curve. And that's a problem, because that means that the galaxies that you're seeing are bigger than all of the ingredients that you think gravity has been able to assemble. So it's no problem if you don't use all of the ingredients, but it's a big problem if you use more ingredients than you have available. That means something's broken. And the more we push this toward high redshift, the worse that it gets. So here's what we had found with Hubble. The lines are, again, kind of the ingredients that you should be able to get at each redshift in these different colors. And the points are the galaxies we actually see. And we see the more we go to high redshift, the worse this is. There are too many, too early, too big galaxies to be able to make under our understanding of the physics involved. And this was the picture with Hubble. Well, now we've just started to get the first results from Webb. So just as we can find these dropout galaxies that I was showing you with Hubble, here's an example of one of the first dropout galaxies we found with James Webb. And these are much redder bands, but it's exactly the same technique that you see the object in the center of the circle. Again, it disappears in the 2 bands on the left, and we see it in the bands further on the right. And so this is a really high redshift dropout galaxy, probably around a redshift of 13. And if we start playing the same game with those and comparing them to what's available, well, now it's gotten even worse. This gray line is the same line I was showing you before. What are all the ingredients that we've been able to assemble? We're well above that line with those black points. And then you could say, well, maybe we can be more optimistic. You know, we said that in the Milky Way, only 10% of the, the baryons get used in stars, 10% of the ingredients. What if we use 100% of the ingredients? Well, that would be the black line, and it's actually still too massive. So there's really no good way out. If this holds up, what that's going to mean, if we discover in the next few years that this result is correct, it's going to mean something really fundamental has to change, because it's going to mean that gravity alone is not enough to assemble the galaxies we see. We need another long-range force that brings things together. And we only know of 4 forces. 2 of them, the strong and weak force, only matter on the scale of the nucleus. One of them, electromagnetism, is really powerful, but that's why things generally are neutral. So it doesn't really matter on these scales. And gravity is what we're left with. So if gravity is not enough, we're going to be inventing a new force, and that's going to be really exciting. But before we jump to that conclusion, we should think back to this iceberg problem. Because the other possibility is that maybe there's not as much iceberg below the surface as we've thought, and we've been overestimating all of these masses. And in particular, you remember this initial mass function that I was pointing out, this distribution of stars that you make at formation. Well, we've been assuming that all galaxies have the same IMF as the Milky Way. But if we think about it, that means they have the same conditions in star-forming regions. So the Milky Way forms stars at around 20 Kelvin. Well, we can work out what happens if you change the temperature of a cloud. And as the temperature changes, the IMF changes. If it turns out that stars in other galaxies don't form at 20 Kelvin, if it turns out they form at higher temperatures, like the blue example, then it's much more, then you don't make nearly as many of these low mass stars, and there's not that much mass below the surface. Okay, well, so that's a good question. Do stars in all galaxies form under the same conditions as the Milky Way? Well, we don't know, but maybe we can try to take a guess. So measuring gas temperatures is really tough. There may be a dozen different galaxies total outside our own where we've been able to measure gas temperatures. But dust temperatures are much easier because dust has strong infrared emission. So you can just observe in the infrared and get the dust temperature. And if we look at dust temperatures, well, these are not constant at all. These actually have a bunch of really complicated dependencies. So we see that the dust temperatures, for example, in different redshift panels, they're different. But within each redshift, again, the dust temperature is not constant. So it's really getting higher toward the top left. So it's getting higher toward high star formation rate and toward low mass. Or maybe a better description would be if you describe some kind of efficiency, like a star formation rate per unit mass, that would point toward the top left corner. The more efficient a galaxy is at making stars, the higher the temperature it is. So maybe that just tells us that all of these young stars that are being made and heating the galaxy, that's really what drives the temperature. But the point is, this is not constant. And if you look at the colors, this is almost never the 20 Kelvin it is in the Milky Way. So maybe we've been getting all of these masses wrong. So what our group's been trying to do, and it actually unfortunately took us about 5 years of work because everything happened slowly with this, but we said, well, let's take all of these templates, but let's add one more parameter in addition to all the other ones we have. Let's add one more in each of these templates. Let's try them at a range of different gas temperatures and see if we can actually measure the gas temperature in these galaxies and measure the initial mass function. Now, the trouble is you need more information to measure more things. So, I mentioned that I've been working now with this catalog called Cosmos, where we have 2 million objects in it. Most of them, we don't have enough information. What we found is you can only recover the temperature for maybe the few percent brightest objects in the survey. But the really good news is if you start with 2 million objects, a few percent is still a lot of objects. We can still measure this for almost 100,000 objects, and we can learn about these temperatures. And so what do we get? Well, the first thing we get is we get a characteristic temperature. So like the other things with the main sequence, there's some characteristic way that galaxies are growing, and it's generally not 20 Kelvin. In fact, if we compare kind of the gas, on top, with the dust, below, we see a lot of the same things. We see it's biggest toward the top left. We see there's some dependence with redshift. So maybe the gas and dust really are doing the same thing, which maybe makes sense physically. But maybe most importantly for our purposes here, if you look at the most massive, highest star formation rate galaxies, like you'd expect early in the universe, the highest redshift ones, toward the panel on the right, they all have temperatures much higher than the Milky Way, which means we've been overestimating their masses. And so if we go back and we take these new James Webb galaxies, but we fit them, allowing the gas temperature to have an effect, it moves these black points all the way down to the red ones. So we go from completely impossible, no way you could assemble the ingredients for this at all, to, well, maybe this is just okay and everything looks normal. Now, this is one example. We now need to do this with, all of the examples that we're getting from James Webb. So, stay tuned. If I have a chance to come back in a year or two, I'll be able to give you a better answer for whether this is a general result or we got lucky with this couple of examples. But there are at least hints that maybe the key to this problem is this recognition that the Milky Way is very different from the conditions that are typical of the earliest galaxies right as they formed. So finally, I want to show you one other thing which we're just starting to learn about. So something completely new that has not been published yet, so very few people have seen. So the other thing we want to do with these gas temperatures is we were thinking about how we learn how individual stars work. And the Hertzsprung-Russell diagram, where we just take a bunch of stars and we plot them in temperature on the x-axis here against luminosity, or maybe you can think about that luminosity as how efficiently they're burning up their fuel on the y-axis, has been a great diagnostic for learning how individual stars behave, how they compare with each other, and the tracks they take over their lifetime. So what we said is maybe we can make one of these tracks for galaxies as well. Now that we have temperature, let's do the same thing. Let's make a track where we take all of these galaxies and we compare temperature on the x-axis with efficiency, so like a star formation rate per mass on the y-axis. And like an HR diagram, they don't completely lie all over the map, but they lie only in specific places. And it even looks like you might get a track that individual galaxies follow. So as we go from the top right to the bottom left, galaxies become more massive, they become older. There's a time dependence. So at the top here at low redshift, there's more of the bottom left, the end of the track. At the bottom at high redshift, we only see the beginning of the track. So it really looks like maybe what we're learning is that galaxies follow this entire track. And the reason that, we only need a couple of pieces of information to tell us about how galaxies are growing their stars might be that there really is one dominant way that all galaxies grow, and they're all kind of following a similar evolutionary track, rather than all, kind of being individualized different histories. And maybe the one last thing I'll kind of mention that's new here, there are really three behaviors on this track. Most of the galaxies are in the top left corner. Those are our typical star-forming galaxies. And then there are the two edges. So the bottom left, I think, is easy to understand. This is where the star formation rate falls off. So I mentioned that galaxies eventually die. These are the dead galaxies. They turn off, and that doesn't make the temperature drop to 0 because there are other things like old stars that still heat a galaxy. The top right-hand corner is the puzzle, though, because these have very high temperatures. And normally you would expect that at a very high temperature, the immediate effect is that it kills the star formation because it's too hard for gravity to overcome the thermodynamics. Higher temperature, your ideal gas law just tells you this means there's more outward pressure. You need a lot more gravity. But the idea we had is to think, wait a minute, if this is right at the beginning of the formation process of a galaxy, maybe what's really happening is that in the central regions where it's very dense, gravity can still win. And so I have to throw one more nice picture of a galaxy up here. Maybe what this is telling us is that top right-hand corner, this early star forming phase just forms the center of galaxies. Then the typical star forming phase is the disk. And the nice thing about, kind of having a big survey with millions of galaxies is that people point Hubble at this field as well, which means we've got pictures of all these. And so we just took some pictures from the top right, the top left, and the bottom left. And here's what they look like. And these are all at the same redshift, which means the same angular scale here is about the same physical radius. And what we see is the ones in the top right-hand corner really do look like they're compact and maybe just forming cores. Then the typical star-forming galaxies, now are sort of maybe getting older in the center. They're getting redder, but they form the disk. And then finally, they become dead. And so this track turns out not just to be a track in properties, but also a track in morphology, even though we didn't have any of that information when we put it together. So the idea is that maybe this is the story of a galaxy, at least observationally. We're now working on this theoretically. And so I think the last thing I'll leave you with is an excellent summer student I had just this past summer, Riley Tam. So what she did was to take one of these galaxy evolution codes, but to change it so that we could kind of get all of this feedback right with the initial mass function and star formation. And here's what one of her runs looks like. And you can see it starts first forming just stars in the center with a nice blue core. Then later it's going to form stars like this disk. And then finally, you're eventually going to see that the galaxy dies and just becomes red everywhere. So I think kind of the conclusion is that there are now two sharp puzzles that we're going to figure out if, whether something's broken or maybe whether kind of we're starting to solve them in the next couple of years with James Webb. First, there's this question to keep an eye on, and you're probably going to see, because there are stories that come out in the media about this occasionally, about whether these early galaxies are so early, so massive that something's broken, or whether it turns out to be okay. And then this other question of, are the first galaxies really like the local galaxies we see and like our own, or are they characteristically so different that means we had been getting the wrong properties? So let me thank you again for inviting me, and I guess maybe take some questions.
Thank you very much, Charles. That was fascinating. And that was an article in 2003. So you just published it last month?
Yep. Yeah, that one. Yep. So one of the really nice things about astronomy is that essentially everything in the field, even before it formally ends up in print, ends up on the preprint archive. So if you go to arxiv.org, you'll be able to see essentially everything in the field. It's almost like turning on a fire hose. There are like 100 papers a day or something. But you can see everything that's happening in the field. And so that 2023 paper is actually one that is on the archive, but still being refereed to appear in a journal.
I see. Perfect. Thank you very much. What a fascinating talk. And let me let the audience know that, well, the floor was open during the talk for questions, and you did ask some, and now more time for questions. Also, let me check in with the people in person if they have any questions to begin with. There are a couple of questions right now. You mentioned about the metallicity of the stars. So are lower metallicity early stars hotter than the other ones?
Oh, that's okay. That's a good question. So lower metallicity, it is true that a lower metallicity star that otherwise has the same mass should burn a little bit hotter because it changes the heat transport. But one of the things that we found about sort of these initial mass functions, which I think was a bit surprising, is you need surprisingly little metallicity in order to get an initial mass function, at least in the simulations, that looks like that of the Milky Way. So it seems like less than 1% of kind of the carbon and so forth content that you get in the sun is enough to still kind of make a similar set of stars. And I think we see that in some local dwarf galaxies.
Perfect, thank you. And there's also a question about Fred Hoyle. So was he right?
I think you have to be a little more specific, sorry.
Okay, so I guess I will ask the questioner to tell us more about what they meant. Because that's what the question is. Okay, and there is one other question about the shape of our own galaxy. Would James Webb help us, be more sure about the shape of our own galaxy? A little bit
That's a good question. So I think the thing that's most successful for learning about our own galaxy has been Gaia, which has had this amazing ability to catalog basically every star. And that's been an enormous advance. I would imagine something like James Webb is going, well, so I think what James Webb will probably help us with the most in our galaxy. I have a good friend who primarily studies dust and the interstellar medium. And one of the points that he always likes to make to me is that every time you launch a new telescope, whatever you think you've built, you've really built a dust telescope. That everything kind of depends on this foreground. And that's part of why the initial mass function in our own galaxy is tough also, is because you can count the stars that you see, but understanding all the selection effects about what you can't see and what's obscured and what you have to fill in is where it becomes so difficult. So James Webb will be better for that, but I think Gaia is probably going to be best for learning about the Milky Way. And James Webb, it's actually in many ways tougher because we're kind of inside the galaxy. It's actually tougher to get the structure of our own galaxy right than it is to get extragalactic things right.
Thank you very much. Are there any questions from the audience in person?
Hold on, let me ask. Yes, sir. The question is, what's high redshift?
Sorry, I couldn't quite hear the question.
It's about the redshift scale. If you can explain the numbers, exactly what they correspond, and if it's higher, is it more redshift, or further away or closer? Did I get the question right?
Yeah. So higher redshift means kind of further away, earlier in time. And to give you a rough idea of what this looks like, a redshift of, when we're looking at galaxies at a redshift of sort of 6 to 8, you're now looking at maybe 1 billion years after the Big Bang. So something where, and now the first galaxies that we're seeing with James Webb are something like 300 million years after the Big Bang. So we're seeing reported redshifts out to about 14 or 15. Now, these are things where we'd like to get some confirmation from spectroscopy to be really certain that after all, once you realize that a galaxy might look different, you also worry about whether you fit the redshift correctly. But if we get that confirmation, it would mean that we're starting to see galaxies a few 100 million years after the Big Bang. So meaning when the universe was like 2 or 3% of its present age.
Thank you very much. Barbara, are there more questions from the audience?
Let me ask, any other questions? The follow-up question is, how old is the Milky Way?
I'd like to have a better answer to that. I mean, I believe at least there are individual stellar populations that seem to be about as old as anything that's out there. One of the things that we see in the Milky Way is that we can kind of see that it's been built up over time. And this is one of the things Gaia has really been helping with. So we can find that the Milky Way didn't form all at once, but there are some stars, in fact, relating to kind of what I was showing here, stars toward the center of the Milky Way seem to be older. And for a while, even there were as we were getting the cosmology right, there was even a problem, I want to say around 50 years ago, there was even a problem where when we looked at the oldest stars in the Milky Way, it seemed like the oldest stellar populations in the Milky Way were older than the age of the universe. And now that's been resolved. So we know the Milky Way, at least some stars formed very early. But there are also parts of the Milky Way that are much younger or even that are still forming stars. One of the things we've learned with Gaia is that there are additional parts of the Milky Way that formed elsewhere and kind of fell in later. So there's a whole complicated history of how the galaxy was built up. And I think the answer to the age of the galaxy is it's complicated. But the oldest parts are about as old as the universe.
Thank you. I don't see any other hands up.
Okay, so let me bring a question from the Zoom audience. It's about the fate of the dark matter after it has done its job of helping form things. Are there any indication that the dark matter has dispersed with age or condensed, or does it remain in the same distribution?
That's a really good question, and that's something we've put a lot of effort into trying to discover. Because if you can discover what the dark matter does, then that would also be a way of learning more about what it actually is. So one of the things we know about the dark matter in not just our own galaxy, but local ones, is that much of the dark matter extends far beyond where the light of the galaxy is. So we often describe kind of a dark matter halo around the galaxy even. And similarly, whereas galaxies often end up flat, there are various dynamics that kind of flatten them out. The dark matter, again, seems to more be spherical. So I think the best thing I could say there is sort of that dark matter is consistent with having nothing but gravitational interactions. And what that means is it's very difficult for dark matter to clump together, because normally the way that stuff clumps together is it gets close, and then there's an angular momentum problem. Unless you can get rid of your angular momentum somehow, you just slide on by. So the way that this happens, for say an electron, is the electron gives off light, it loses energy, it slows down, and that gets rid of some of the momentum. Dark matter doesn't get to do that because it can't give off light. And so one of the things that we're still trying to understand is, does dark matter truly have no interactions other than gravity? That seems unlikely when you try to make a good particle physical model of it. Or does it just have some really weak interaction that maybe we can find some relic of that would change the distribution a little bit? And so one of the ways people have been studying this is they try to look for the dark matter distribution in the centers of galaxies where things are very dense, Because the idea is if you only have like a really weak interaction that particles have to be very close, the denser it is, the more likely it is that you're going to get those collisions and you're going to see something. But to this point, unfortunately, we've spent the last few decades knowing that dark matter exists, looking for different ways to probe its properties, and being unable to directly find any evidence so far that it does anything other than just kind of pure gravity. So we're still pretty sure it has to, but we haven't found it.
Thank you. And now a question about the very research that you're showing in right now. If I'm correct in interpreting it, it says that the galaxy, when you mentioned that the star formation starts from the very center, and you probably have simplified it very much. So am I correct in saying that the stars, like it's a ring of radius, and then it starts forming the outer and outer and outer stars? Like this?
At least approximately that's what looks like is happening. I think, there are a couple other effects you see here where like there are some density waves that you can maybe pick up and things like that. But this is also coming from a simulation, and the nature of simulations is that you're picking kind of as much of the physics and as high resolution as you have time to run on your computer, and kind of hoping that you've picked something representative. So I think this is probably more a proof of principle that the story is plausible than kind of something more direct.
Yeah, so then the follow-up question is that since this is done in 2014, has there been any more like fine-tuning to the simulation, maybe considering the effective presence of another galaxy nearby or anything of that sort?
Okay, so this is actually not 2014. This is a paper that we're still working on. The 2014 is the original code that we sort of took and modified.
Okay, okay.
So we're still exploring this and exactly trying to answer these questions. So it's a really good question, and if I get a chance to come back in a year or two, I think I might have an answer. But this is literally where we're at this moment. Not yet having written it up.
Sure, thank you. And there is another question about the putative relationship of the SMVH and the galaxy mass. If I'm understanding the question correctly, can you elaborate?
Okay. So we do observe that the supermassive black hole at the center has several relations. One relation with kind of velocity dispersions of things near the center. There's another relation with the total stellar mass. And so we do observe that's something which is true for galaxies. So presumably that means the growth of the supermassive black hole has to be part of this same story and has to be part of this same feedback track.
Perfect, thank you. And I do not see any more questions from the Zoom audience. Any more questions from the in-person audience? Barbara?
I think we may have a couple. Do you have a question, John? Do you want to come up and ask it rather than have me relay it? John Hoot has a question.
So eventually you converted the different initial mass functions to some sort of standard. Where did you come out? Saltpeter or Kruger, or where did you end up, or what units do you characterize them in?
Oh, okay. So the question was, I guess, which IMF we'd actually picked. So for the study I showed you before, where we just picked a standard, we ended up picking a Chabrier IMF at the time because that was the one that kind of seemed easiest to us. For the modeling that I'm showing you here, we picked a Krupa IMF. And the reason we picked a Krupa IMF is that it's a little bit easier physically to understand. So a Krupa IMF, the way it's derived, it's a little bit easier to understand how that should change with temperature. than some of the other IMFs.
I think we had another question here. Oh, you mean okay. We have a comment from an audience member here that he would like to see this presentation about 10 times over. Is it going to be available on the website?
Yes, Charles has gracefully agreed to let us publish his talk, so it will be available on our YouTube channel, and you could find the link to our YouTube channel at the footer of every web page of our website.
It's on the web, on the home page. No, you go from our website. Yeah, we had a navigation issue. Any other questions? Am I missing anybody? Okay, I think we've got everybody from here. And thank you very much, Dr. Steinhardt. We've been enjoying it.
Thanks for inviting me. It's been a lot of fun.
Thank you very much. So before we go to end this session, could you tell us a little bit about this summer research program that you're doing? And those who are interested, what should they do?
Sure. So there are two different programs actually that we run. One that kind of works through the Caltech SURF program and kind of related things where we make a deal directly with universities. And then there's another National Science Foundation funded program. So there are a bunch of NSF summer research opportunities, some domestic, some international research programs. So the NSF program, the deadlines have passed for all of those for this year, but you can look out for those going forward. And there's not just one here, but there are a bunch of different programs. I know the Hawaii one, for example, is very well run. The other thing that we do is we kind of make deals directly with universities as well, like we have one with Caltech's SURF program. And we have a student from Minnesota, for example, coming this summer. So that's one where people are welcome to get in touch with me directly, and I can see whether we can set something up with your university.
Perfect. Thank you very much again, Dr. Steinhardt, for a wonderful presentation. I hope you see the kudos coming your way in chat and on Zoom. And before I end the meeting, I would like to remind everybody that you could check our calendar on the website for all upcoming events at ocaastronomers.org. Thank you for joining us, and we wish you a great time ahead. Bye-bye, everybody.